Good afternoon, everyone. I'm Deng Chenghu. I'm truly honored to have been invited to present the work for Qing Wang, Jing Wang, Yuhao Zhang, and Professor Jiwu from Tsinghua University. In networked stored system, clients manipulate data in the stored server connected via the network. Conceptually, clients post the stored request and obtain response. This work explores how to achieve extremely low latency for stored requests. The most common way to handle the stored request is the remote procedure call, or RPC. With RPC, a client first sends a request. Then the server CPU obtains the request, executes it, and finally returns a response to the client. As the latency of the NIC hardware gets lower and the throughput gets higher, the server-side CPU becomes the bottleneck of latency in the RPC approach. The latency introduced by the CPU consists of the two parts, the queuing latency of the request in the RPC queue, and the request execution latency. To eliminate the server-side CPU latency, another way to communication is through the RDMA one-side verbs. Specifically, a client sends a request via RDMA read or write to access the data in server memory. At the server side, the RDMA NIC executes the writes or reads by DMA operations, and finally returns a response. In this way, the latency included by CPU software is avoided. However, one-side RDMA will include the multiple RTTs, offsetting the latency benefits of bypassing remote CPUs. The reason behind this is the limited semantics of one-side RDMA, which are restricted to simple read and write operations. For example, as shown in the left figure, when a stored system contains index like B plus tree, clients must perform index traversal and pointer caching, inducing many round trips. Another example is a scenario where there are concurrent access, as shown in the right figure. To resolve the write-write conflicts with one-side RDMA, clients need to access the data with synchronization primitives like locks. It will trigger multiple RTTs such as acquiring and release locks. In addition, if we want to use the RDMA one-side verb, it needs to heavily refactor the code to modify the traditional RPC mechanism to one-side access. In this work, we want to get the latency advantage of both the RPC and the one-side RDMA at the same time. We start by processing a property called Wire-Latency. For a stored request, it is Wire-Latency when it only needs a single network round trip and its crucial path bypass the server-side CPU. Then we ask, can we achieve the Wire-Latency for general stored requests? If a stored request can be realized in a Wire-Latency manner, it must meet certain requirements, such as not returning an execution result. This is because a Wire-Latency request is committed without waiting for the server CPU to execute. We find the new externally property defined by a recent work perfectly describes the requirements. A stored interface is neo-externalizing or neo-ext if it doesn't not externalize its effects or system state immediately. It just returns an acknowledgement indicating committed, rather than returning an execution result or error. Neo-ext interfaces are common in storage systems. For example, in Memcached, set is neo-ext. In RocksDB, put, delete, and merge are neo-ext. So we can execute them asynchronously on server CPU, which makes latency neo-ext request possible. Here, we use a set operation in Memcached to show our basic idea. First, the client issues an RDMA write, which contains the set command. Then the server NIC writes the command to memory and return the ACK. The server CPU executes the set operations asynchronously. In this example, the critical path of the set operations is wire-latency, one round trip with remote CPU bypass. However, the challenge of achieving wire-latency NeoX request is maintaining linearizability in the presence of multiple clients. The challenge is hard to address, since the execute NeoX request is asynchronous and the responses are generated by NICs. We use an example to present the challenge. Let's consider the three clients A, B, and C. First, the client A writes a command set key value 1 to the server and get a response from the RDMA rat. Then, the client B writes a command set key value 2 to the server and gets response. After these two requests, the client C issues a get key. The get operations is non-NeoX, so the server CPU must execute it asynchronously and returns a software response. Based on the physical time sequence of these three operations, the correct linearizable order is set key value 1, set key value 2, and get key. But how does the server CPU know this order and execute accordingly? Only they will get the operation return the correct result. Unfortunately, with RDMA write, the server CPU cannot get the correct linearizable order. This is because RDMA one-side verbs lack the ability of the inter-client coordination, and the clients must specify the destination addresses of sent data. Therefore, server CPU doesn't have enough information to obtain the linearizable order. It is a common view that bypassing a remote CPU must be done using the RDMA one-side verbs. We break the common view by re-examining what it means to bypass a remote CPU. For an RDMA write, when pulling the completion signal of an RDMA write, the client can guarantee that the data will reliably reach the server memory. How does the client obtain the guarantee in a remote CPU bypass manner? By further looking at the hardware mechanism of NICs, we found the property of bypassing the remote CPU result from the ability of NICs to generate the hardware ACKs, independent of the type of RDMA verbs. Specifically, when offloading reliability, server NIC generates the hardware ACKs to confirm safe delivery. Upon receive an ACK while pulling CQ, the client can obtain the guarantee. Using the observation, we use the hardware ACKs from two-side verbs to achieve the wire-latency NeoX request. We propose the ordered Qing abstraction, which leverages the rich Qing to produce the linearizable order. OQ abstraction consists of the two rules that define how the server-side NIC and the server CPU interact with the RQ, respectively. In NIC rule, NIC allows receive buffers in order and return the hardware ACKs. In CPU rule, CPU executes the requests in order and return the response for NeoX requests. For clients, they use the hardware ACKs for commit signal of NeoX requests and the software response for the non-NeoX requests. Using the above two rules, storage systems will generate a linearizable order that follows the position of the received buffer in the RQ, even using the hardware ACKs as response of NeoX requests. Let's use an example to show how OQ works. Suppose the backend storage system is Memcached. Initially, at the server side, the RQ is empty and the Memcached instance contains a key pair, key value 0. Then a NeoX request sets key value 1 arrives at the first buffer on the RQ, and the RNIC returns a hardware ACK indicating the committed, achieving the wire latency. After that, a new X request set key value 2 experiences the same process with the second received buffer. Then the RNIC receives a new X request get key and places in the third buffer in RQ. At this time, the CPU asynchronously executes the request in RQ in order. That's the slide. After the CPU has finished executing the first two requests, it executes the get key and returns a software response containing the value 2. As shown in this example, with OQ abstraction, the correct linearizable order is consistent with the positions of buffers in RQ. Then we built the Juneberry, a communication framework that implements the OQ. The interface of Juneberry is like RPC, but the client can mark a request at Neolix and use the hardware ACK as its commit signal. Juneberry uses the two sides send and receive on RC mode, and it is centered on shared receive queue so that different clients send a request to the same server-side SRQ. To support multiple CPU cores, Juneberry adopts a simple data partition schema currently. Specifically, in the server, each worker threads creates an SRQ and maintains an exclusive set of datasets. For clients, they send a request to the correct SRQ according to partition schemas. For storage system that contains persistent states, Juneberry supports durability by leveraging emerging persistence memory technologies. First, Juneberry put in SRQs in persistence memory so that requests in SRQs can serve power outages. Second, Juneberry makes the hardware acts as have the persistence guarantee by flashing PCIe buffers at the server side. Due to time limit, I omit the other design detail in this work. If you are interested, please check the paper. We also evaluate the Juneberry using a cluster of the one server machine and 8 client machines. The servers are equipped with the OptimPM. All machines are connected by 100 Gbps RDMA NICs. We first evaluate the performance of Memcached caching system Memcached. Client threads generate requests at a given rate with the portion arrivals. We select the 4 representative in-memory caching workloads from Twitter, and the table shows the result. The Juneberry reduced the medium latency by up to 90% and 83% against the eRPC and the deferred X. This is because Juneberry eliminates any software delay in the crucial path of the set requests. We then evaluate the performance of a persistence key value store called the PMemKV value. We set the object set to 91-byte workload flow of zip5 0.99 access distribution. From the two figures on the left, we can see that Juneberry reduced the medium latency and how when the workloads are read intensive, Juneberry has higher latency, as shown in two figures on the right. This is because when supporting the durability, Juneberry places RQ to persistent memory, which increases the access overhead of requests. Finally, I give a brief summary. In this work, our goal is achieving the wire latency for storage requests. Our key idea is repurposing hardware X of NICs as the commit signal of new X requests. This work demonstrates that making storage software has a visibility into network-level knowledge can bring performance benefits. Thank you for your listening. And for more details, you can check the paper or connect it with the author of the paper. Thank you all.